Hello, friends and mentors. I am Jayesh Patel. This is my webinar series number 18. It is about PD monitoring of gas insulated substations. This topic is very important, relevant, and important topic in the present time because there are issues of getting space for new substations, especially of air insulated substations. We don't have any option. Only option left is to go with the GIS, which needs only 20 to 25% of the area or space required as compared to AIS. Last but not the least, by physical inspection, it is not possible to pinpoint any fault or sparking, etc. in the GIS. The only monitoring device available in the GIS are the gas pressure of different modules and compartment that can be monitored. Therefore, the PD sensors are provided by all OEM for PD monitoring. I am very delighted to share that the subject matter expert Jayesh Patel Ji is with me, and we are going to discuss the same matter. Before I invite him, I would like to say a few words related to my mentors and family, and from the core of my heart, I would like to thank my family, my well-wishers, my mentors, my supporters and friends. First of all, Almighty, my family, my parents, my wife, my son, my mentors, respected PPY sir, KK Murthy sir, KK Gupta ji, NK Mittal ji, P Ramachandran sir, S. Pao sir, Hitesh Chauhan ji, Dr. Kamal Bansal sir. The list of my friends and well-wishers, the names comes that is very first is Saket Gupta, Arvind Tukral ji, Dr. Vikas, SK Batra ji, and Vishandan ji. Last but not the least, my team working day and night for making this to happen includes Gulab and Ramdhani. Now time to introduce today's speaker Jayesh Patel ji. He is a great performance solution leader South Asia in the Mega. He is a person with overall 25 years of experience in handling various test and measuring equipment in electronics and electrical segment. He graduated as electronics engineer in 1996 from Pune University, and he started his career in 1996 as technical sales engineer, handling instruments from brands like Tektronix, Agilent, Yokogawa. He gained expertise and knowledge by working with research institutes like Bhabha Atomic Research Center, Tata Institutes for Fundamental Research, and manufacturing organization in the field of electronics and embedded software. Later, he diversified his ever-growing field of electrical from 2003 by associating himself with brands like Mager, and then he dived into the subject of SF6 gas handling and thermographic by further expanding horizon with brands like Dilo and Slade. In January 2020, he joined Mager Power Diagnostic and driving growth for grid performance and solution verticals in the regions of South Asia. He's a person having specialization in the partial discharge testings and monitoring solutions for various electrical assets. If we talk about the personal front, he is a avid traveler, enjoying outing with family and friends. And now, without wasting further ado, I would like to hand over this stage to Jayesh Patel ji. Welcome to my platform of Igniting Power Engineers, and the stage is yours to set the stage on the fire with your knowledge. Welcome, sir.
Thank you very much for the lovely introduction, and I thank all the participants and the platform of Igniting Power Engineers to allow me to give a presentation out here. Without wasting much time, I would like to jump onto the presentation. Let me share my screen with you.
It's visible, sir. Please continue.
Yeah, it's visible. Yeah. So if we talk about partial discharge, let me first go through the agenda. What is our agenda of today's presentation? So we would be touching upon the topics of partial discharge in GIS, little bit about the basics about the partial discharge in GIS, the unconventional partial discharge measurement technique, which is used for PD measurement in GIS, touching the topic of sensitivity and high voltage testing, which are the standard commissioning tests associated with GIS, and then the maintenance strategies and temporary monitoring facilities or the functionalities used to analyze and diagnose the partial discharge and then further take on the actions to rectify and increase the reliability of the gas insulated substations. So let's first understand when we start with the topic partial discharge. Why partial discharge measurement? Because we have been doing several measurements in GIS, like monitoring the gas density, checking the gas quality, or doing the breaker timing measurement, breaker contact resistance measurement. Why we need to do a partial discharge measurement? Why there is a need to do this particular measurement? So if we understand little bit why it is required, it is the most common reason. The partial discharge is the most common reason for deterioration of assets insulating system, because everything what we do in today's modern world about the measurement in electrical asset is to keep our insulating system intact, because if the system insulation is good, the system will operate for prolonged period of time and there will be less hassles in the operation. When partial discharge occurs, it gets associated to a term long-term degradation of insulation. The degradation of insulation starts, and once PD occurs, and if it is left undetected, then it continuously increases because there is no halt or stoppage. It is a gradual acceleration process. So these are the reasons which are contributing to a fact that some measurement is required for this phenomenon called as partial discharge. And if it is undetected or not measured, then it will worsen the insulation condition, which will lead to failure or asset works less efficient and can lead to a total breakdown of asset, which is GIS in this case, and which could disturb our daily operations for several weeks or days, and it is directly associated to loss of revenue. So these are the most common facts and the reasons why partial discharge measurement is of most important in GIS. Let's understand something about basics of partial discharge. I will touch upon few things because that only in future will be discussed. So if we talk about partial discharge, or if we talk about the GIS, then as we see, there are three important components. One is the central conductor or a high voltage conductor. Then there is a outer enclosure, which is a ground potential. And in between this conductor and the enclosure is filled up with the gas, which is the insulating material. Now, in general condition, this insulating material is designed in such a way that by design it is a homogeneous electric field. The electric field across the GIS is quite homogeneous, and the strength of this electric field is just below the critical field strength, and hence everything is functioning smoothly. In case of certain imperfection, like as we see over here on the central conductor, the electric field strength at those particular point increases above the critical field strength, and that is where the inception of the partial discharge happens, which could be associated with some sparking mechanism inside the GIS. Now, whenever the partial discharge occurs in GIS, there are good and bad things associated with it. It is good, it is bad also. Now, if we talk about good things, it is that electromagnetic emission takes place because of this dissipation of energy, and which is in a form of radio waves, light or heat, and sometimes also an acoustic emission. And the good part about is that whenever this emissions takes place, it is measurable. We can use some detection methods and we can quantify this emission, and hence we can measure the quantum of partial discharge. And the bad part associated with partial discharge is the deterioration phenomenon, that once PD occurs, the insulation starts deteriorating and it is going to accelerate over a period of time, and then gives to birth called as phenomenon called as aging mechanism. Now, just measuring the partial discharge is not something where we have to stop or which is going to help us. We also need to understand that this imperfection which is causing partial discharge is happening where inside the insulation, and it is happening because of what reason inside the insulation. So once we know these two things, where and why, we can have certain detection mechanism or take some precautionary mechanism and schedule a maintenance work so that we can increase the reliability. So these are the reasons why we should measure partial discharge. So ultimately we can track down, do the maintenance and increase the reliability of the operating GIS. When we need to do a measurement of partial discharge, we need to use some detection methods. So as we see over here, whenever this partial discharge occurs in any insulating material for XYZ reasons, it gives birth to various physical phenomena, and which can be detected using various detection methods like optical, mechanical, electrical or chemical. But not all the methods are useful for measurement of partial discharge. Now suppose we take an example of optical method. In this method, what will happen that the optical detector will definitely measure the light or the spark which is generated by the partial discharge, but the optical detector in this case has to be close to the phenomenon, that is it has to be close to the source of light. If it is happening in one compartment, the light cannot be transmitted into another compartment, so the measurement is restricted if it is happening only into a particular compartment. So it's a limitation. We cannot use as this method uniformly across measurement in GIS. Similarly, there are some limitations with respect to chemical method, and hence we zero down that there are two usable methods which can be used for detection of partial discharge in GIS. The first is acoustic. Now, acoustic measurement method can be used for detection of certain deformations in partial discharge, but acoustic cannot be used for continuous 24/7 monitoring. The reason, it is susceptible to noise, can be easily disturbed, and some specific kind of measurement tools and noise elimination techniques have to be used, cannot be implemented continuous monitoring, and it is limited to only particularly manual measurement with some portable instruments. However, the electrical UHF measurement method, UHF means ultra high frequency measurement method, is the most reliable method which can be used to detect each and every type of partial discharge defect happening due to various reasons. And this is universally accepted. The UHF measurement method is universally accepted as the right method to do the partial discharge measurement in GIS. If we understand there are few reasons why this partial discharge happens or partial discharge occurs in a GIS, and the obvious reasons are certain defects. One of them is a void, which is a permanent failure or a permanent issue into the hard structures. Could be a free moving particle inside the GIS which is left unattended during commissioning, or it would have entered during evacuation and filling of SF6 gas. A fixed particle or a protrusion onto the surface of the GIS, or could be a poor contact electrode which could have been not aligned properly or would have misaligned due to some vibrations of because of breaker operations. So these are the few reasons because of which the partial discharge phenomenon starts or happens inside the GIS. Partial discharge phenomenon results due to the discharge current into any insulating medium. And this discharge current could provide a different signature in different insulating medium. So whenever we talk about partial discharge in SF6 gas, why we say the UHF method is useful, it generates a pulse, a discharging current pulse, which could be having a typical rise time of 100 nanosecond, and if we convert that into a frequency spectrum which could range up to several gigahertz. And the frequency spectrum from upper higher frequency range of hundreds of megahertz to gigahertz is called as the ultra high frequency band. And that's why we call that the sensor technology used is a UHF sensor technology. Now, if we take the same partial discharge, if it is happening in nitrogen or any other gas, the typical rise times could be of the order of nanosecond, and it will generate a frequency spectrum only up to few megahertz. And that is why it is a medium frequency range, not a ultra high frequency range. So maybe it is the discharge which is happening in the respective insulating material, which will result to a spectrum which will lead to a particular frequency band. So every partial discharge measurement in UHF band or in medium frequency band is needing different type of sensor technology and different type of measurement mechanism. Let's understand about some signal propagation whenever a partial discharge occurs into the insulating medium or inside the GIS. So as we know that PD activity emits transient electromagnetic waves, and these waves will travel across the GIS, and GIS enclosure will act as a waveguide which will guide this wave to the different part of the GIS, which will cross the barrier insulator and will cross and enter the next compartment also. Now, these signals are a broadband signal, and this signal, when passes through GIS, they generate complex signal propagation. Now, when we say complex propagation signal, because in earlier diagram we saw GIS as a very good waveguide and having a very good structure, like a simple highway is the straight highway. But that is not the case when we talk about the real geography or real geometry of the GIS. It is similar to what we see on the right hand side top of the diagram. It has got a complex structure inside those gas insulated switchgear tubes, and they basically provide various reflections and signal attenuation when the emitted signal pass through different portions of the GIS. This different diameters of GIS basically act as waveguide and provide an impedance or a variable impedance to this emitting signal. And as we know that whenever there is signal transmission happening through any medium, it encounters change in impedance, it reflects certain amount of waveform. So each change in diameter of this GIS enclosure or a waveguide will reflect certain signal back, and there will hence there is the back and forth reflection of the partial discharge signal. Even the rough surface influences the signal propagation through dispersion. So net effect is that the GIS partial discharge, which actually should have been a nice single pulse, result into a pulse packets which are due to these reflections. And these effects are highly frequency dependent. That means certain portion of the GIS will reflect certain frequencies, certain portion of GIS will reflect certain frequency, and hence this PD pulses is converted into the pulse packet. So it is not a single pulse, it is a packet of pulse. Since it's a packet of pulse, it contains various frequency components which could having a different attenuation or different reflection, and hence our measuring instrument should be having a wide band measurement. It should not be measuring a frequency of a typical particular spectrum, but it should be a wide band measuring instrument providing a good sensitivity to the entire GIS. That means the measurement bandwidth should be from 100 megahertz to 2000 megahertz. And here, not a single coupling capacitor is used like a conventional PD measurement, but multiple UHF sensors, as we see out here, are placed inside the GIS or embedded into the GIS, which are used for this electromagnetic waveform measurement. These UHF sensors acts like an antenna and convert the electromagnetic wave into the voltage signal, and which are ultimately fed to the measuring instrument. When we want to do this measurement, there are various types of UHF sensors available into the market or can be used depending upon the type of GIS which we are using. Starting with an ancient or vintage GIS which are already there in the field but did not have inbuilt UHF sensor. So if you want to do this PD measurement in this kind of GIS, then we have something called as external flange sensor. Now these external flange sensors are retrofitted without opening the GIS on unshielded spaces. So there are spaces which are unshielded and which offer certain openings. So these sensors are placed onto this opening, because if it is a shielded portion, shielded metallic portion, then this UHF signal will not radiate out of the GIS, and hence it has to be placed onto this unshielded spaces or unshielded portion of the GIS, from where it will pick up the signal and then it can be fed to a measuring instrument. Since it's an external arrangement, it offers lower sensitivity. There are certain old GIS where you have window sensors or the inspection windows are available, like this, which are generally used to see inside the GIS if there are any visible indications of some deformation. So this window can also be used for connecting Windows sensor. We have a Windows sensor available, so which can be retrofitted into this kind of GIS openings without opening the GIS, can also be used for partial discharge measurement. The only criteria which needs to be taken care is that the window diameter should be more than 60 mm. Then only the useful PD radiations can be captured. Otherwise, not all the partial discharge frequency spectrum will be captured and we will have half information. Again, this being an external element offers lower sensitivity. Now come to the today's generation GIS, where it is already loaded with integrated or embedded UHF sensor, something like this, and which is spanning a frequency range from 100 or 200 megahertz to 2000 megahertz, which is providing a broadband measurement response. And since these are integrated into the GIS, now this is the portion where we see on the screen is an antenna which is embedded into the GIS, and outer connection is only the N-type UHF connection, which is used for doing the measurement or capturing the signal. So since it is embedded, the antenna is embedded inside the GIS, it provides best signal to noise ratio. The only thing required is that you have to ask the manufacturer to provide this inbuilt UHF sensor. So that is something which you need to take care whenever you're going to buy new GIS. Much often in 110 or 220 kV or 400 kV GIS, the manufacturer will provide you these sensors. But if you have any lower rating GIS, then you have to ask manufacturer to help you with this inbuilt UHF sensor, so that in future you can use them for partial discharge measurement. When we say inbuilt UHF sensors, then the question comes where these sensors have to be placed and how many quantity of sensor is to be placed in the entire geometry. And this is described or guided by a standard or a paper written by Seagray. The older form of Seagray is TF 15/33.03.05, and it is redefined or rewritten as TBA 654. Now, these are the two documents which talk about the sensor placement and the measurement which we do with the sensor. And the procedure is called sensitivity verification. Now, this sensitivity verification, it's a two-step procedure, and it is used or it is set up as an acceptance criteria for accepting any GIS, and it is almost like a calibration like procedure. So let's see what is this sensitivity verification, because much often today, tomorrow, or whenever we are going to come across subject GIS, then the two important aspect of GIS acceptance are sensitivity and HV test, which are very much to be known, and we should know exactly how measurements are performed and how we should accept this GIS. So as we saw, it is a two-step procedure. So first is a verification step 1, which is performed in a laboratory. So here parallel measurements are performed in a laboratory. One, as per conventional IEC 60270, which is a horizontal standard explaining the measurement procedure of partial discharge. And then the second is an unconventional UHF measurement. So these two are performed parallelly onto the portion of a GIS. So if we have selected a portion of a GIS by manufacturer, they would place the sensors on the certain portion of the GIS, and just under the sensor, they will inject or they will put a artificial partial discharge defect, which in most of the cases is a moving or a floating particle, and will apply high voltage to this GIS, and the high voltage will be raised. So now two parallel measurements are happening. One is a conventional measurement where we will measure the discharge in picocoulomb, and the second is the UHF measurement, which we will measure the voltage captured by this UHF sensor. So we will raise the voltage and adjust the defect in such a way that the electrical measurement as per IEC 60270 conventional method will measure 5 picocoulomb, because that is the acceptance criteria. So once the equipment measures 5 picocoulomb, we will note down the UHF pattern captured by this UHF sensor and the voltage recorded by this UHF sensor. We will remove this artificial defect, and at the same point we will use a pulse generator or an artificial pulse generator, and we will inject a variable pulse into the same UHF sensor. Again, we will keep on increasing the voltage or a pulse of this pulse generator till this UHF measuring device will record the same voltage level and the same pattern. Once we recorded the same voltage and same pattern, we come to a conclusion that the pulse generated by this artificial pulse injector is generating the same effect of partial discharge which otherwise my original PD source would have generated. And what we achieve is a pulse voltage which is equivalent of a 5 picocoulomb partial discharge. So these results which we obtain are valid for a particular type of GIS using a particular type of sensor and a particular type of pulse generator. They are valid for a particular setup. Now we have received the data which is in terms of pulse, which is equivalent to generate the 5 picocoulomb discharge. The step 2 is done on site. Once the GIS is shipped on site, it is assembled. We need to again perform the sensitivity check that whether my GIS is sensitive enough to react to a 5 picocoulomb partial discharge. The procedure is that we carry the same pulse injector on site. We will inject the same voltage pulse into a particular sensor. Now, as we see from this gas SLD, there are 1, 2, 3, 4, 5, 6 sensors which are there in a particular bay. So we will inject a pulse into a one particular sensor, and we will check the sensors into the surrounding area. That means we will connect measuring instrument to the surrounding sensor, and what qualification required that all this nearby sensor should read the signal, some part of signal above this noise floor. It is not that it has to read exactly the same amount of amplitude, but it should react to this particular pulse. That is the first criteria, and it is again extended to the next nearby sensors. This way we have to check every measurement path of the GIS. Now once we have injected pulse at this portion and we measured response at this sensor and this sensor, we can say that the point between sensor number 2 and sensor number 4 is qualified to capture 5 PC pulse. If the pulse is applied here, both the sensors are capturing. If PD in origin is shifting to sensor number 2, the pulse at sensor number 2 will respond with a higher magnitude. And if PD is moving towards sensor number 4, the point number 4 will result with a higher amplitude. That means the PD, if anywhere happening between point number 2 and point number 4 to a quantum of 5 PC, any of the nearby sensor will respond, and hence we can say the path between point number 2 and point number 4 is clear to capture 5 picocoulomb partial discharge. This way we will inject pulse to the next sensor, we will measure at correspondingly the next sensors in nearby vicinity, and we establish an acceptance criteria that this particular GIS is sensitive enough to capture 5 picocoulomb and above partial discharge if happening anywhere inside the GIS. So we have set up an acceptance criteria for the GIS. The sensitivity verification confirms that the given measurement setup is capable of detecting all PD impulses of 5 picocoulomb and above. Now, unless and until each sensor is passing this particular criteria, we should not let GIS charge, because if the GIS is kept on working condition, then we may lose out certain portion of GIS bay which is not sensitive enough, and if PD is happening in those particular area, none of the sensor will pick up. So the important criteria is that each of the sensor should pass this acceptance criteria for 5 picocoulomb, because Segrè states that the sensitivity offered by the inbuilt UHF sensor should be good enough to capture this 5 picocoulomb partial discharge. The second important test in GIS is a HV test, because generally whenever GIS is tested, the sections are tested in the factory or in the site, because if we test the entire GIS, we need a very big power supply. Hence, it is always tested in section and it is passed through various test cycles. So the voltage is ramped, it is kept constant, called as conditioning of the GIS, and then it is raised to a maximum acceptable voltage of a GIS, kept there for some portion of the time, and then it is again reduced to a conditioning voltage, and then a partial discharge measurement is performed to check whether any PD is happening under the high voltage influence. During this measurement or PD measurement, it is very important that the synchronization should have been done to the supply voltage or the operating voltage, because if you measure partial discharge data and if it is not synchronized with the phase, then you will not get a proper PD pattern, because as we know, PD pattern is nothing but a PRPD waveform, which is like phase resolved partial discharge pattern. So phase is the important element of information which is always needs to be fed whenever you are doing a partial discharge measurement. Now, whenever we do HV test mode, generally the instrument is parallelly connected on all the channels and the recording should be performed, where an instantaneous PD is recorded into the scope mode, and then the data is recorded in form of PD and the high voltage, because as we talked earlier, some synchronization is required with the high voltage, and the same data our instrument can also record. So as we see in all this parallel measurement window, we have a scope mode where instantaneous PD value is measured. We have a recorder mode where PD value and the high voltage are recorded over a period of time. They are recorded as a stream. So at any point of time, this green volt is a voltage input and this blue is a partial discharge. So we know exactly during the entire cycle of HV test, if during at particular voltage my PD is exceeding the desired level. Like here on the right hand side, some sensors we see that during the maximum peak high voltage, the PD is generated. Although it may not be very important because it is happening at the extremely high voltage or the maximum voltage which we are applying, but it is always good to know that the PD is occurring because of what kind of defects getting exposed in the GIS. So we will see in the next slide what additional measurements are also performed parallelly during HV test. But most important that this HV test is recorded for the trending and PRPD, and this can be used during future events to compare what was the reading or what was the behavior during HV test. And it is very important where you can compare the behavior pattern of new GIS and the old age GIS. So as we seen, you can record all channels parallelly. If a defect is being observed, we can switch the mode, and along with this recording, wherever there is a PD, we can also record the PRPD pattern. And when the PRPD pattern is recorded, the defect can be easily interpreted or defect can be easily known. So during this HV commissioning test, all this data are recorded parallelly: the instantaneous PD, the partial discharge inception voltage, extinction voltage, applied voltage, and the PRPD, and that becomes a fingerprint of your GIS which can be used in future. So when we do all these tests, now the question comes, what kind of information this will give you when you do this PRPD measurement? So all this defect decreases the withstand voltage of GIS. Whenever the PD occurs, they will basically reduce the withstand voltage of a GIS, and a high percentage of failure can be detected when we do this partial discharge monitoring. So if there are about 10 type of errors or 10 type of malfunctions which are happening in GIS, all of them will contribute to some partial discharge or some discharge phenomenon, and they all can be monitored if we are doing a watch onto this partial discharge voltages. So the failures which can be detected by PD monitoring are mobile or moving particles, the protrusion, loose or floating element inside the GIS, particles on insulating material, if there are some dust particles onto the insulating material, voids in insulating material or the cavities inside the spacers, contact erosion, or defects in GIS components such as VTs, CVTs, or any other. And if we see these defects, so they are either visible during the commissioning or the early year of operation, or they will start appearing during the old age or wherever the wearing of GIS happens. Generally, the GIS is quite stable unless there is some unfortunate event happens during the continuous operation period. Let's see some of the errors which are captured and the effects which are seen with PRPD pattern. So first we can see is the contact problem. So we see whenever this kind of problems were captured, the corresponding PRPD patterns, and when the GIS was opened, we could see what kind of problems we could face or we could see with this kind of particular pattern. So we have captured those data and segregated. So it is quite easy for any user to understand the cause and analysis. So if there is a PRPD of this nature, it indicates there is a contact problem, and this is something which you can see visibly when you open the GIS. Now this particular pattern is due to the faulty disk insulator, and if it is not taken care, we can see this sparking which has happened inside the GIS. Right hand side pattern is something which is generated because of the moving particles, and if we see down below with the visible eye from the monitoring window, we can see there are some dust particles which are there moving inside the GIS. Now there is a video which is visible over here. I'm not sure whether you can see, but this is an example of moving particles. So if there are any dust or metallic particles which are there inside the GIS, then they start playing or they start dancing under the influence of high voltage, and they will jump from the GIS level or the conduct tilt towards the conductor, and they will create a path between the ground potential and the high voltage potential, and they act as a catalyst to create the sparking inside the GIS. Now, if we talk about the partial discharge phenomenon, now we know how PD occurs, why PD occurs, what kind of PD occurs. So let's see how you can measure the partial discharge in GIS. So in GIS, the partial discharge strategies could be: first is no PD, you don't do any measurement, you are relaxed, you are not exposed. You do offline PD testing, that is a commissioning test, that means when GIS is not charged. You do online PD test using a portable instrument, but it has got some plus and minus. You do permanent PD monitoring, that means a 24/7 monitoring system can be installed onto the GIS, which again has some plus or minus. That means the PD measurement could be available in three forms, like offline PD with the high voltage applied externally, online PD with portable, and permanent. But when we say a portable instrument, again you are limited by the individual manual operator skills to analyze and understand PD, but it offers you a flexibility that you can take it to a multiple asset and you can do a PD measurement. Also, it's cost effective. When we talk about a permanent installation, that means 24/7 monitoring system, it is the best form of PD measurement, but it offers lesser flexibility. That means if you have a multiple assets, you will need multiple systems, and they are quite costly. So both the world, like portable and online, are offering its own plus and minuses. So what Power Diagnostic or Megger as a company, we have developed a new platform called as temporary partial discharge monitoring, which offers you best of both the worlds. So you have a portable instrument, yet it offers you all the measurement possibility of a permanent monitoring system. So let's see in the next slide, what is this solution? So we have a portable instrument. It can be connected using an casing, which can be used in case if you want to leave this instrument for monitoring in outside of the switchyard. Otherwise, you can connect the same instrument for a temporary monitoring. The setup is like this: you have this GIS, you connect all measurement channels to your portable instrument, and the portable instrument is connected to a software. Now, when we say software, our portable instruments are equipped with the software which is 100% same as what we provide in a permanent monitoring. That means it can do a spot PD measurement, it can do a trending on all the channels parallelly. Wherever there is a PD, it will record the PRPD patterns, what you expect from any recording device. And it is not only stopping as a recording, because if you have an 8 hours recording, you cannot look out where the PD is occurring. You cannot go through those recordings. You need some alarms, which is generated like an online monitoring system. So this is the next screen. So all the sensors are connected parallelly. The system is measuring partial discharge, and the alarms can be set. So whenever these alarms are raised, a PD will be captured and the PD event will be recorded. Like if we see here for a particular UHF sensor, if we click on alarm, a particular PRPD pattern will be shown to you. So the benefit is that you can leave a portable instrument unattended on site, which will do recording, which will raise alarm and generate all the required inputs, so that it can be completely unattended system like your online monitoring. Yet it is flexible enough where you can carry it to a different assets and keep the different assets on monitoring whenever you are in doubt on particular sensors. Once we have this partial discharge pattern captured, we can see here there is an ICM expert button. So once we press this button, next software screen is available, where original PRPD pattern will be captured with the database and the result will be populated with the matching pattern. So if you are a new user or if you are not exposed to the pattern analysis, there is a software you help which will be always about 95 to 98% accurate in terms of its interpretation. Moving forward, this device, a portable device, can be connected with the mobile communication interface card, and this can allow to access or monitor the partial discharge instrument through a cell phone via internet from any remote location. So if you are in one location or you are in your office, and if the instrument is in say XYZ substation, still if it is equipped with mobile communication interface, you can access the data and you can monitor everything like you are in front of instrument. So as we see, GIS partial discharge is relatively simple as compared to PD in transformer, because you have a limited amount of defect in terms of floating element, moving particle, protrusion or void. These are a very common defect in partial discharge. Like if you have some connection issue, or if you have some loose connection, the pattern will be generated similar to this, and they will be mostly related to zero crossing voltage and would be generating an vibration at typically 100 or 120 hertz. And if the gap between this loose connection is more than the electric field of insulating material, then it will start the inception of PD, and then you can actually see a different kind of PRPD pattern. So if it is not crossing electric field, you can capture using acoustic sensor. If it is crossing electrical field, then there will be a partial discharge which you can capture using UHF sensor. Now there is a simple example when you do a parallel multi-channel measurement. Sometimes people say we have one channel instrument and it is good enough to do PD measurement. Yes, theoretically it is possible to connect from one sensor to another by using a single channel, but there are advantages of using multi-channel together. Like if we say an example of a typical case study what we had at a particular substation, so where a PD alert was generated by the instrument and it was on R phase, like we see a signal over here. Now fortunately it is a multi-channel instrument, so we see there is the same pattern which is acquired on Y phase as well as B phase of parallel sensor, and which helps us to understand there is the same signal which is on R phase, which is translated or which is coupled to Y and B. So on particular sensor, say sensor point number 4 on R, Y and B, all three phases the pattern is observed, which is more or less similar. So we zero down that there is little bit difference in amplitude related to R phase, and cross coupling is happening to B and Y. So now we know that on R phase there is some issue, B and Y phase are reflecting the issue but to a smaller amplitude, so it's just a cross referencing and not a problem. But now on R phase, where is exactly the problem? In particular sensor, left side wala sensor mein or right side sensor? We move forward, and if we have parallelly the same measurement done on those sensors as well, then we can compare the position on R phase of sensor number 1, sensor number 2 and sensor number 3, and we can say yes, 2 and 3 are capturing less amplitude of signal but similar nature, and point number 1 capturing a higher amplitude of sensor. So yes, on R phase, sensor number 1 is typically expected to have partial discharge which is in the vicinity closer to position number 1. So we've seen a 6-channel or typically a 9-channel measurement would really help you that in one shot you can zero down to a source of PD, and that is important. Now if you do the same thing channel by channel, then you will not have this correlation and you will be practically left blank in terms of your measurement relative solution. Same in case of moving particle. If we see this kind of defect which is called as moving particle, then what we need to do is to apply another technique called as acoustic technique and understand that these moving particles are jumping to what height, because the electrostatic force makes this particle jump towards the HV conductor. That means from the base of a GIS they will jump under the influence of high voltage, and when it will touch to the high voltage conductor, the breakdown will happen. So whenever it is moving particle, as a user we should always measure the bounce time or the length to which the particle is bouncing, so we exactly know it is going to touch the HV conductor or it is not going to touch the HV conductor. and that is generally done by using acoustic. So whenever we see a moving particle signature, immediately we deploy our acoustic sensor at various positions on the GIS, and we capture the particle or bouncing particle pattern. So either of the sensor will give you an amplified pattern, and then on that particular pattern, this is what we are going to see. So if we do a measurement between a particular vertical height of the bouncing particle, we can convert that into a measurement using this formula, and exactly we know the height at which the particle is bouncing. So that gives you an idea whether immediate action is required or the bouncing particle is not going high enough, and I can still wait for some period of time to monitor this activity. So whenever you have a pattern for moving particle, the next action what you need to do is apply an acoustic sensor and measure the bounce height. So probably your measuring instrument should have not only UHF measurement technique, but also should support acoustic measurement. So in such kind of defect scenario, you can also do a measurement of height of the bouncing particle. So these are the some more example of PRPD pattern what you can see when you have a protrusion. So whenever it's a protrusion, the effect is more seen towards the peak of the positive or negative cycle, because during that time the PD level are higher. If it is a void, the pattern could be similar to this, which is dense at the edges and that is less dense inside the envelope. This is the typical pattern of void. So different kind of mechanism or different kind of error generate different kind of patterns in partial discharge, and analyzing these patterns will give you the indication that what could be the probable source of partial discharge. So by doing this analysis, you can come closer to your problem, and then you can decide whether any immediate action required. If suppose for a GIS of 100 channel, you are finding PD on 5 or 7 or 8 channels, then you should not immediately jump to a conclusion that let me open a GIS or let me take a shutdown. The next action, what can be initiated is use an instrument with the temporary monitoring feature and put those channels where you are observing PD for a trending over a period of say week or 10 days or a month time. And if you are getting consistent partial discharge result, then yes, next step is to really take a decision and move forward that yes, these are a serious partial discharge patterns and I should take some action so that the reliability of the GIS is not disturbed. So with this, I would like to end my presentation onto the partial discharge of gas insulated substation, and the participants to open the session. In case any of the session or any of the measurement techniques, if we have any doubt, then yes, you are most welcome and I would be more than happy to address those things.
Sir, thank
Over
you.
to you, sir.
Sir, thanks a lot for this wonderful, exciting presentation from your side. And it is very much required so far. This GIS is required because without doing the partial discharge monitoring, you can't survive, because you can't check the health of the GIS you are using in your system. And you have made 100% effort from your side, and hats off to you for your wonderful presentation. Now you take rest for 2-3 minutes, and I would like to invite my mentor PPY Saab. Kindly I unmute and give your feedback, then we will go with the question answer.
Hello, Rajesh. Yes.
Yes, sir. Please.
Are you getting me, Rajesh?
Yes,
my
yes,
voice?
Yes, sir.
Yes, sir. Good evening to you and all my friends who are listening me. At the outset, I must congratulate you for this wonderful 18th webinar. Quite a good number. I think you have scaled up quite a big number, now 18. I think in the days to come, you are going to still scale up. I think the number, you're doing a lot of work. And my congratulations to Jayesh Patel. He is a stalwart in the power industry, doing a wonderful job for Megger and particularly on the subject of GIS PD measurements. So what I have to say, as very rightly told by Rajesh, as we are advancing, you see the system and the systems are getting complex. There is a need of such technology, of course, GIS. GIS, we have a lot of knowledge. GIS, we have a lot of knowledge. But GIS, maybe we gained quite a bit of it, I think, in the last 25, 30 years. But I think there is a more need of getting such knowledge from the experts like Mr. Jayesh Patel to accentuate. As I know, you see, the subject he has covered is wonderful. This is partial discharge testing, then including an unconventional PD measurements, HV testing, then the maintenance strategy. Because the maintenance part is really difficult. Fault finding part of GIS is really very, very difficult part. And exactly as Mr. Patel has brought it out, the testing is going to help a lot, and we are definitely going to be benefited with the today's presentation, and I'm sure all my friends who are listening, they would have gained a lot. This is an excellent presentation, and he has explained it in a very lucid manner. Hello, Awaz Jari? Are you
Yes,
getting
sir.
me, Rajesh? Rajesh, are you getting me?
Yes, sir. Yes, sir. I am getting you, sir. Please continue.
Okay, so continue. Okay, I was not getting the picture. It is explained in a very lucid manner, and all the has made to make the presentation a really very nicely done up and wonderful presentation, I must say. And not only that, at the end, I must say once again that we are really proud of our friends like Rajesh Arora ji and the today's speaker, Mr. Jayesh Patel, for giving us the best. Rajesh, I know day in, day out, I don't know whether he's sleeping these days or not, but I think for the last couple of months and a year or two, I can rather say, he has done a lot of hard work to disseminate the knowledge. And I love people who are versatile. And he's doing a lot of versatility, a lot of things he's bringing out for us. So no words for him to honestly to appreciate Rajesh. And I am sure in the days to come also, he is going to really help the nation, all the professionals, and we are going to be beginner. And before I close, I once again give my special thanks to and gratitude to Jayesh for doing a wonderful job today
Thank
for
you, sir.
us. Thank you so much. Thank you so much.
Thank you,
Thank you
sir.
so much.
Thank you very much for your words of appreciation and blessings, because your blessings matters a lot. Sir,
Thank you so much.
coming to basic questions that people want to ask on behalf of all the participants, I would like to start with few questions. I have noted down because the presentation was very, very exciting and wonderful, mind-blowing in fact. Sir, my very first question, you have mentioned that PRPD many times in your presentation. Why this PR is required, phase result, partial discharge is required to get the pattern?
Sir, if we see any PRPD, what happens that a partial discharge pattern, let me make it clear that if anyone has seen a PD pattern, so it is not a frequency scale, it is plotted between 0 and 360 degree. A background is a sine wave, and then in front of sine wave we have some dots which are plotted and the signature is created. So what happens that whenever a PD is captured, it is captured as a single point of information, and on the sine wave of 360 degree, that information is plotted at a particular phase which is synchronized to your supply or operating voltage phase, and the PRPD is captured for a period of 1 minute. And then at the end of 1 minute, the plot is something called as a populated dense information of PD dots, and that is what we call as a PRPD pattern. So if we remove out the phase information, we don't know how to plot it, because it is phase versus the amplitude, and that is why it is called as a PRPD pattern is phase resolve partial discharge pattern. So the phase is the important essence of pattern. If phase is not there, then there is no correlation between the data and we cannot analyze the pattern.
Very good, sir. Sir, I have noticed one thing in the beginning of your presentation. You were talking about the good and the bad impacts of partial discharge.
Yes.
Can you please elaborate more on the good impact of partial discharge again?
Yes, as I said, every side has two coins. So whenever we say good part, why I said good? Because partial discharge is obviously bad, because ideally it should not happen. But since it happens, the good part is that it discharges some energy. Because if PD is happening and if there are no evidence of physical things happening, then we cannot quantify, we cannot understand, we cannot measure. So whenever we say the discharge happens either in any form, in electromagnetic waves or heat or chemical changes, we can quantify, we can use some sensor technology to do a measurement. That's why I said there is some good sign of it, that it emits something which is measurable. And when there is something measurable, we can quantify and take analysis and take decision based on to that. So that's always some good part which is associated with partial discharge.
Okay. And further, you elaborated about the portable, temporary, and the fixed continuous monitoring. You have explained that in the temporary monitoring systems, you have to use the same kit that will be working as a permanent for some time, for a day, for example. But do you think it will give the same results that we can expect from the permanent monitoring system?
Yes, sir. In our case, I would say 100% same, because that's what I said. We have worked on that platform that maybe if you take year back, we also had the two platform, a portable instrument, its own software, which will do a spot testing and you can do analysis. A permanent monitoring system, which has its own analysis strength and which has got alarms. So it is completely unattended. It takes its own intelligent call on the partial discharge pattern based on to the algorithm, based on to the alarm stored, and it is the best form of instrument. But we know that it comes with the cost. So if you have a multiple assets, or in the same substation, if you have 3-4 different level of substations, like 400 by 220 by 110, then you need 3 systems, and it's a fantastic amount of cost which goes in. So people were reluctant to have this kind of cost or this kind of investment, but still they wanted some benefit. So we invented, or we added a facility called as remote server into our instrument, and we are providing the same software to our portable device, which is there for the online. So the software is same, 100% replica. So you can use the portable instrument, connect to your GIS, and the software background remains the same. So you can set alarms, you capture PRPD.
Sir, but it has one issue. When you talk about the portable instrument, it has limited channels of 3 or 6.
Yes.
That can take care of a particular section of modules, not the
Yes.
entire system. How
Yes.
you can compare it with the that having the more 100 channel or 150 channels, depends on the size of GIS.
Absolutely. See, we promote we advocate a concept that in case you don't have budget, see, if you have a budget, online is the best. But if you don't have budget, so what people do that on quarterly basis, they carry out the PD measurement with portable spot. And if you gain some sensors where you are getting doubtful signatures, or if you are getting PD, then you can only put those sensors onto the monitoring and have a better call on those sensors, because
Yes.
those PD is something which is not going to happen overnight. It is a gradual process. So on some portion it would be captured, some portion which are clean, so you can leave them out of measurement. So yes, with that limitation, we have 8 channel options available, which can be gradually extended up to 40 channels, a portable version. So you can have that kind of monitoring still possible.
Okay, tell me one more thing, sir. You have mentioned that they are PD by imperfection. Can you elaborate what do you mean by imperfection? Because the imperfection start with the manufacturing process, and can during transportation some defects can ignite, can start that PD in my system. What your view?
Yeah, see, imperfection is in 2 cases. First is the voids. which are a part of manufacturing process imperfection and which can never be taken out of GIS. They will be there. So they will be exposed first during the HV commissioning test. So you have to really understand whether this is acceptable. If it is very minor, you can take a call along with the manufacturer whether to accept or whether you want to replace. They would be probably mainly into the barrier insulators or spacers because it's a hard manufactured product. The second imperfection is during the commissioning or maybe during evacuation and filling of SF6 gas. So if proper care is not taken, then some dust particles, some metallic portions can get inserted into this GIS. So this is another imperfection.
What about the transportation? My question was related to transportation.
Transportation, if it is an imperfection, that could be typically a loose connection, and that can be easily captured or addressed during HV commissioning.
Okay.
Because during HV commissioning, if they are visible, then you can always open again, take care of them, and you can still go away with that.
Coming to the very relevant question of interpretation of understanding the spectrum of PD and the pattern. You always say use some software. Every manufacturer say use some pattern, but what I feel as a practical engineer, it is difficult to understand that pattern by going to the data bank you are providing the software. But every time we have to be dependent on the instrument supplier to understand the spectrum of a PD. What do you say about it?
Not always, sir. That is an initial setup because see, as I said in my presentation, in PD, in GIS is relatively simple. There are 5 or 6 common defects and you can easily remember or master those patterns. If you make a chart and stick in the instrument library, it is quite easy, relatively quite easy. They are simple enough.
Can I use the same instruments if I want to measure the PD in the transformer?
You can, with the input that what technology the equipment is supporting. Suppose you have an equipment which is supporting only UHF technology, then your transformer should have been equipped with UHF sensor. Then yes, it is possible.
Otherwise not possible.
Otherwise not. Suppose
at the last side phase of your presentation, you mentioned that to understand some pattern, you need acoustic sensor also.
yes.
But most of the utility have changed their specification. They are going with UHF only.
Yes.
And how to go back to that acoustic again, or how we have to go with the equipment having capability of UHF and acoustic? Is it possible?
Possible, sir. We have both the type of instruments, 2 generations. One only UHF.
I'm not talking about a particular company.
Yes.
Yes, because
It is. Yeah, I'm sorry. It is definitely possible, and it is a need of a measurement. See, one is a possible, one another is a need. Suppose you have a moving particle, which is a very common phenomenon which is happening in GIS. Then how you decide that moving particle is at which location? Because once you identify moving location, you should know whether it is in my bus bar, it is near to some moving component. If it is near to breaker chamber, then yes, I need to take care of it immediately. And as we know, moving particle will start bouncing towards the conductor under the influence of high voltage. So if I have to take immediate action, then it is to be like the conductor tak wo pahunch raha hai ki nahi pahunch raha. If the bounce is high enough, it is going to touch the conductor, then I have to immediately today I have to take a call. So for that, we have to use an acoustic measurement to exactly locate the position of the bounce and know the height of the bounce. Then only you can decide.
And final question, can I use the same instrument for my cable termination like cable, or I have to adopt some other technology to check the PD in the cable?
Yes, cable GIS is quite simple because GIS cable would be terminated into a particular chamber. So if those chambers are equipped with the UHF sensor, which in most of the cases are, then your UHF measurement equipment will definitely capture this pattern.
Will it take care of the PD in the entire cable, or some extent? To some extent, it will measure.
To some extent, because cable is a long piece of instrument. So if the PD pulse is good enough and it is traveling till the UHF compartment, then it will take care of it. Because ultimately the signal should reach to a sensor. Sensor is not going to walk down to the signal.
Last question. Last,
Yes.
you have mentioned many times 5 picocoulomb is
Yes.
standard testing criteria. Why
Yes.
this 5 picocoulomb? Any idea?
Yeah. See, every asset, sometimes transformer, sometimes cable, sometimes GIS, or maybe rotating machine, there's some standards have been set that what is acceptable level of partial discharge, because we cannot say at first day it would be zero. There would be some level of partial discharge. So what should be the acceptance criteria on day one? What is the bare minimum acceptable? So SIGRE 654 is the standard which has laid down those guidelines, and it says in GIS 5 PC and below is acceptable. So you should worry only when the PD is more than 5 PC.
Thanks a lot. And now I invite everyone, kindly raise your hand and you can ask question directly. I have covered many of the relevant questions. If you feel some more question to ask, you can raise your hand. Neeraj ji, kindly unmute. Neeraj Singh ji, please.
Sir, I wanted to know the synchronization. You are talking about the different channels. How you achieve in your kit?
Sir, synchronization is a very simple. Every PD instrument has a synchronization input. So this synchronization input is basically connected with the VT signal, which you could receive from anywhere inside your substation. Basically, you have to provide the same voltage signal which is being fed to your GIS to this synchronization, so that the phase information is obtained. Because if you have only direct PD information, then phase information intelligence has to come from outside, and this is where a synchronization input to the instrument is going to help. So yes, most of the instruments available in industry today has got an external synchronization input available, and this has to be a separate input apart from the measurement channels, which is generally called as a sync input also.
Sunil sir, kindly unmute. You are welcome.
Thank you, sir. Very nice presentation given by Jayesh, sir. Just
Thank
I
you.
would like to ask one question, that whether same instrument can be used for measurement of the partial discharge in the transformer.
Very good question, sir. See, when we talk about partial discharge, because here I have not gone into the basics, there are 4 different methodologies which are used for measurement. The first is a conventional PD measurement, which is like measuring the partial discharge in picocoulomb by connecting instrument directly to the device under test. And this can happen only by connecting a coupling capacitor across the measurement device, which is called as the electrical method of PD measurement or IEC method of PD measurement. Second is a UHF method of PD measurement, which is done by using a inbuilt or external UHF couplers. Third is using a acoustic measurement by using a acoustic sensors. And fourth is by using a HFCT, the high frequency current transformer, which is coupled to a grounding terminal of any device, and you can capture the PD signal. So PD can be measured by these 4 methodologies. So when we say GIS, 99% it is UHF. In some case, it is UHF plus acoustic. In case of transformer, all 4 measurement methods are possible. If you have an inbuilt UHF sensor installed by manufacturer into the tank, you can use the same instrument and use the UHF technology. Acoustic is simple because it is always using an external acoustic sensor mounting on the tech of the transformer. But if you want to do a physical measurement in IEC method by connecting coupling capacitor or using the bushing tan delta point of an instrument, then your measuring device should be equipped to capture this kind of signal. Because normally I have seen the instruments available in the market are supporting 1 or 2 technologies. So if you want to have a more flexibility, you should have a measuring instrument which will support all 4 measurement methods. Because transformer is the device which will make all 4 measurements possible. It is up to the user which method he wants to imply and how he wants to make connections. So idea is that you should have a versatile instrument which will support the measurement methods. So in PD, it is reverse. In other cases, like first we choose the equipment and then we see how we will do a connection. In PD, first we have to choose the measurement methodology, and then we have to choose the right instrument which is going to support this measurement methodology. So yes, as a manufacturer, we have few models which will support only UHF and acoustic. We have few models which will support all four measurements. So it is you as a user have to pick right instruments depending upon the assets which are available with you for measurements.
Thanks a lot. Any more question? Kindly raise your hand. Otherwise, I would like to stop. We are running out of time. Any question? Kindly raise. Don't miss the opportunity. I think all questions have already been answered, and time to say thanks to Patel Saab for sparing your valuable time and accepting my invitation for dissemination of knowledge on this very important subject of partial discharge of gas insulated substation. With that, thank you, sir. Thank you once again. Thank you, sir.
Thank you very much for this
Everyone
platform
for
and the
sparing your time.
opportunity. Thank you very much. Have a
Thank
nice weekend. Thank you. Bye.
Thank you.